Good morning. Let's start now. In the last 2 days, we started looking at a compiler's backend and we started looking particularly at machine dependent stuff, optimizations as well as code generation as part of the lower end particularly. If you remember, we had said a code generator has three primary objectives. What were they? Instruction selection, then register allocation and instruction scheduling. So that's the third bullet which we would see today. We have, if you recall, we looked at some simple ways as well as challenges behind selecting the right instructions for a particular platform, and then we had looked at two register allocation algorithms, one based on graph coloring and then another based on linear scan. Then we also said that, since we have access to the program and we also have access to the hardware at this stage, let's perform some low level optimizations. We looked at optimizations primarily related to memory. We understood the organization of heap and stack and allocation of objects and even local variables on the stack and the heap, and how we could move things from one place to another based on a program, based on what does a particular program do. We looked at an interesting IDFA called as pointer analysis and its applications to perform better memory allocation, right? Or memory allocation that's more efficient in terms of access and deallocation. So we have seen all these aspects. Now the final thing left here is, once you have selected instructions, you have also performed register allocation, perhaps you have also performed some low level peephole or memory level optimizations to generate as good a code as you can. At that point of time, it's a good idea to now decide how to execute this code on the hardware, and that's what comes under the ambit of instruction scheduling or scheduling, whether you want to use the British or the English American pronunciation. Okay, so that's what we are going to look into today. Alright, so instructions, why is even instructions scheduling interesting? The point is, most of the hardware do not really execute code one by one. See, if my hardware just said, I will execute this instruction before this and then the one after this and in serial order, then scheduling is a bit simpler. You just need to come up with an order of instructions. But interestingly, modern hardware, even non-multi-core hardware, also allow you to execute multiple parts of each instruction in parallel, right? How many of you have learned about a standard pipelined architecture? Okay, some of you. We'll just do a brief revision. So in a pipelined architecture, you need not execute instruction number 2 after finishing all the parts of instruction number 1. What are the parts when we execute an instruction? What all things the hardware needs to do while executing an instruction? It needs to fetch the instruction from what part of the memory? The code region, as we had seen earlier. So it needs to fetch the current instruction, understand the current instruction, parse it, figure out what does it need to do, which parts of the circuitry does it need to involve. Let's say decoding the instruction. And then if the instruction requires some operands, where are those operands located? Register. Sometimes they have to be moved to the register, so there may be an instruction that actually fetches an operand from the memory and then puts into a register. Otherwise, if you are already performing some arithmetic operation, then those operands might already be in the register, so they are in the memory. Let's just assume they are in the memory. They are in the register or they are in the cache. Well, even in the memory, they may be either on the stack or on the heap and so on, right? So that's, let's say, operand fetch. Then you really need to execute the instruction. Okay, fine. If it's an add, then you need, or if it's an integer add versus if it's a floating point add, based on that you need to involve the right circuitry in your hardware and then perform that operation either between registers or between register and memory. And finally, if the instruction has some result produced, you need to store the result somewhere. If the result is supposed to be on the top of the stack, like in the Java virtual machine, you need to push it on the top of the stack. If the result requires to be stored in some memory location, you have to perform a write back to the memory, and so on. So you can typically break an instruction into multiple of these parts, and the interesting part is that most hardware have different kinds of units that take care of each of these parts. Okay, loading something from the memory might be different from performing an arithmetic operation, for example, or fetching an instruction might be different from the circuitry for fetching an instruction might be different from the circuitry for decoding what does the instruction do, some logic there which takes a switch case and decides what to do, for example. So typical hardware have different units to perform to execute different parts of your program, and that kind of hardware is usually said to have a pipelined architecture. You can create a pipeline of things and do things one by one. If one part of the pipeline is fetching an instruction, some other part of the pipeline may be executing another instruction, and because of this you can create a lot of parallelization in terms of how the instructions really get executed in your hardware, which gives more opportunity for a compiler to figure out a schedule and order of the instructions in which you can make good use of this pipeline, or you can utilize this pipeline as good as possible. See, when we say utilization, the objective is that most parts of the pipeline are busy doing something useful, right? So if you have an instruction whose schedule or the schedule generated by the compiler generates or lists instructions in an order which keeps the pipeline empty most of the times, and it's possible, if it was possible to schedule an instruction before such that it probably finishes execution, overall the throughput of the system increases and so on, then you would say it's a better schedule compared to the previous one, right? So again, coming up with the best schedule is an what kind of problem? It's an NP complete problem. You can map this problem down to something which is already known to be NP complete and say this is also an NP complete problem. So you can't guarantee that you have an algorithm that comes up with the best possible schedule for all programs, but you can again use some heuristics or some approximations here, some conservative estimates here to come up with a better schedule than a given schedule, for example, which utilizes the hardware better in some sense. So even if your hardware is not multi-core but it is pipelined, you have more opportunity to produce schedules that may be better than a very simple linear schedule of instructions one by one as given in the program order. Similarly, if your hardware is on top of it multi-core, if you have multiple threads to run, if it is possible to actually execute instructions differently on different cores, then you can utilize it even better and you can parallelize your instructions. In the next few days, I'm sure you will also be taught about how could you parallelize instructions on different multi-core as well as GPU hardware and so on by other instructors. Okay, so there also instruction scheduling has a role to play, and a schedule is typically generated by the compiler. A compiler tells the hardware, oh, I want to make sure that in this clock cycle this instruction is scheduled in this particular part of the hardware, and that schedule is used by the hardware to execute those instructions. All right. Some people sometimes get surprised that instruction scheduling is something done by a compiler, not by the hardware. Well, the hardware can do better stuff on top of what the compiler produces, but a compiler also has a lot of opportunity to generate schedules that utilize the hardware better. Okay, so let's take an example here just to understand our pipeline system here. Let's assume our pipeline, the hardware on which we are working, has 5 stages. Those stages are, let's say I am executing an instruction I, then I have the 5 stages: instruction fetch, instruction decode, then operand fetch, then execute, then write back. Now note that this is a generalization. Some instructions may not have any operands, some instructions may have only one operand, some may have 2 operands, some instruction may not read to write back the result to the memory, but typically in the worst case an instruction will have all of these stages, let us say. Okay. And let us, again for simplicity for now, let's assume that each of these stages can be scheduled in one clock cycle. So in order to execute all these 5 stages of some instruction I, let us say we would need 5 clock cycles. In the first cycle we fetch the instruction, in the second cycle we decode the instruction, in the third one we fetch any operands, in the fourth one we execute the instruction, and in the fifth one we write back the result, if any, to the memory. Let's assume this is the structure of this instruction I. Now if I have an instruction I plus 1, let us also assume that all 5 of these stages can be executed independently in my pipeline. So if something is being fetched, something else may be decoded at the same time, and so on, right? So if I have a program consisting of, let's say, 5 instructions, I plus 1, I plus 2, I plus 3, I plus 4, then I could actually utilize my pipeline here, and let me start fetching the second instruction I plus 1 in the second cycle itself, because the fetch unit of my pipeline is empty, it's lying idle. Okay, so I could continue like this. I could fetch the operand of the second instruction in cycle 4, because the OF part of the hardware is, let's say, lying idle, and then I can execute it here. I can write back the result to memory. Then let's say I have 5 instructions like this: I plus 2, I plus 3, I plus 4. And let me just keep filling my pipeline to figure out how many cycles do I need to execute all of these instructions if I have a pipeline architecture available. What would be the number of cycles I need here? 9 cycles. So in 9 cycles, I would have executed, in an ideal scenario here, I would have executed 5 instructions. Whereas if I executed them one by one, how many cycles would I need to execute these 5 instructions? 20 or 25, right? 5 times 5, 25. So 9 versus 25. How much improvement? How much time did I save? I saved 16 cycles, which is like speeding up the program by maybe 2.5 times. Instead of 25, I am able to execute it in 9 cycles. If each cycle is 1 unit of time, then I am able to execute it in 9 units of time instead of 25 units of time, and hence my program would run faster already, right? But now there are interesting things over here. Well, first of all, the simplification was that each instruction has these 5 stages. Some instructions may not have all the stages, so this has to be decided based on what kind of instruction it is. If an instruction doesn't have any memory operation, there won't be any write back, for example. So that's one thing to keep in mind. Secondly, it's not necessary that all these instructions are independent. Can you think of a sequence of instructions such that the second one's result depends, or second one in some sense depends on the result of the first one? Yeah, go ahead. Correct. Any other example?
If there is any label in the instruction, the previous instruction before the label is dependent on the next instruction. At that time, maybe the sequence will.
Right. So there are 2 kinds of dependencies as pointed by what's your name? Rushikesh and Jayashree here. There are data dependencies in my program of the kind Jayashree pointed out. Let's say instruction I depends on the result produced by instruction I minus 1. So let's say instruction I minus 1 does A is equal to B plus 10, and instruction I does X is equal to A plus 5. Now you need A in order to be able to fetch the operands here. So the previous instruction should ideally have written back A to the memory, only after which you can get the operand of the second instruction from the memory, right? Otherwise you might get either a stale value of A, or you may not find A in the memory, you may get some garbage value, and so on. Okay, so you have to wait for the previous instruction to have written the value of A to the memory before getting it. And then, as Rishikesh pointed out, there are also control dependencies. Maybe in order to decide whether instruction I should be executed, you need to find out whether the instruction I minus 1 produces a true or a false. Let's say I have if x greater than 10, then go to some instruction I1. In order to decide whether you should execute I1, you have to wait for the branch to be determined, whether it results into a true or false. If it results into a false, you should not have executed instruction I1. You cannot always go ahead and execute an instruction before determining whether all its control dependencies are satisfied, right? So now, if instruction I plus 1 over here, if its result is required to execute instruction 3, instruction I plus 2, right? Let's say this guy writes to a location A and this guy reads from a location A. Can I schedule this OF stage in cycle number 5 over here? No. So I'll have to wait here. I'll have to stall this pipeline. Okay. I'll have to move. I'll have to, let's say, strike off. I cannot schedule OF here. I cannot schedule OF here. Where can I schedule my operand fetch now? After 6. Let's say over here. And then I'll do execution here. I'll do write back here. Since this operand fetch happens here, and maybe if this result is also required by I plus 3, I'll have to move this down, I'll have to move this further down, and so on. So I may not, this was the ideal scenario, that if there is no stall, in this case I may be able to finish execution of all 5 instructions in 9 cycles. But in a general program, you may have dependencies on previous instructions, either data dependencies or control dependencies, which may allow you or which may require you to create these holes in the pipeline, which are called stalls. Okay. So a compiler can also look at the program and figure out if the next instruction reads something which is written back by the previous one, and while producing a schedule of instructions, it needs to take care of this, right? Now there is one interesting thing here. There are different hardware that allow us to improve on this. It's a general observation that many times if you write instruction I plus 2 after instruction I plus 1, it's likely that I plus 2 uses the results of I plus 1. Okay. So many hardware allow you not to wait until the write back stage of the previous one. See, before the write back stage, what would happen if I have a statement here, A is equal to, as we said, let's say B plus 10, and then you have some X is equal to A plus 5. You remember when we used to select instructions, you have seen this in Java bytecode as well as the kind of assembly instructions we were generating on the first day in the first session. When we generate instructions for this after performing register allocation, won't it happen that before you write back the register containing A into the memory, that register has the value of A? Right? So there would be some register, let's say R3 in this case, let's say our register allocator assigned register R3 to A. In that case, if there is nothing here which occupies register 3 in between, when you reach this second instruction over here, you already have A's value available in R3, isn't it? If it's already there in R3, do I really need to fetch it from the memory location pointed to by A again? No, I could have directly taken it from R3. So when is it available in R3 already? In what stage of the previous instruction would it already be available in R3? Maybe after execute. So after execute, let's say I have finished performing B plus 10, the result is already there in R3. The only thing that this write back stage will do for the previous instruction is to write that value into the memory location A. Of course, you know that a compiler may in fact eliminate a write if later on. So you may also see that sometimes some of these writes do not happen because A's result can be directly used from a register here and then A is written to somewhere else, and so it may decide not to even write it to the memory. But at least for the time being, we can see that after the execute stage of the previous instruction, in this case this instruction, you can directly access its result from the register, and hence you need not wait for fetching your operands until the write back of the previous instruction has finished. You can directly schedule it after the execute stage of the previous unit, right? So there, if a hardware provides such facility, it's called operand forwarding. And if the compiler, of course, the compiler is supposed to be aware of the hardware while generating code. If the compiler is aware that, oh, operand forwarding exists, it may create a schedule such that the next instruction does not need to wait for the write back stage. Its operand fetch can be scheduled a bit before. So we need not push things down so much in case of stalls. Operand forwarding may allow us to directly get the results from the execute stage sometimes, and hence I don't need to really create a stall here. I can do operand fetch over here itself and directly get the result after this execute stage and then here put execute, here put write back, and this one is not needed. So which means I may still be able to schedule instructions in a way that my total throughput is still better. Okay, so this is just an example. There are various other features provided by different hardware. For example, instead of writing back to the memory, see, we had seen what was the difference in the order of cycles required for writing to a register versus writing to some level of cache versus writing directly to the main memory. You remember, some 1 cycle for register, 2 cycles for L1 cache, 5 cycles for L2, 200 cycles for main memory, and so on. So writes to main memory are extremely slow. So various hardware also provide us with something called as, does anyone know, a place where you store writes, a write buffer. Okay, so they also allow us to buffer all these writes into a special hardware before, if into a special, let's say, in a physical hardware unit. Instead of waiting for all of them to be written to the memory, you can get the latest values of some operand that you require directly from the write buffer. Okay, so there are things like this also provided by various hardware, and all these allow us to avoid the impact of stalls to some extent. Okay, instead of, when there is a stall, instead of pushing the stall to too late, you can actually fetch things early on, either from the write buffer or directly from a register, and so on. Okay, so again, all these are under the ambit of a compiler. Based on the knowledge of the given hardware, it can take advantage of all these features and create a schedule which is better than a naive schedule. Okay, so let's look at an example. Of course, you may say that hardware prefetches instructions and so on, so they all work in tandem. On top of what the compiler does, the hardware may be able to prefetch some instructions beforehand and try to, it may also try to speculate a branch and try to do something. Even a compiler can help do so by having more knowledge of the program, and these work in tandem. Okay, they help each other many times, or sometimes they even work against each other, but then one of them should know that, oh, I should modify my algorithm so that it helps the other guy instead of working against it, for example. And compiler designers usually are better placed there, because changing a hardware is difficult, right? You won't write a new hardware typically for C programs, for Java programs, for Python programs based on their different compilers and their different algorithms. Usually it's the compiler designers who can take more advantage, or who are supposed to take advantage of the hardware by writing algorithms for scheduling, code generation, register allocation that are better suited for a particular hardware. It's just a cost benefit ratio, right? You can do things in software without having to ask everybody to buy a new laptop with a new hardware that supports something more interesting. It's more expensive to change things or improve things in the hardware than in software, for example. In this case, the compiler. All of it. Okay, so let's look at an interesting example of instruction scheduling. We would first look at basic block scheduling. What is a basic block? Louder? No, I can't hear you. What is a basic block? Yes, the same control flow graph that one of you was mumbling. Yes, correct. It's a part of a control flow graph where, correct, it would have a single entry and exit. That means you cannot enter the basic block anywhere except in the beginning, and you cannot exit the basic block anywhere except the end. You are supposed to execute all instructions within a basic block in order, right? But now the compiler plays with it. Now the compiler can see that, oh, within a basic block I have 5 instructions, and in order to take advantage of the pipelined architecture as well as features like operand forwarding or write buffers and so on, I can actually order these instructions in interesting manners. Okay, and that's what we would look at when we say basic block scheduling. Like we studied intra-procedural and inter-procedural analysis yesterday, basic block scheduling means schedule instructions within a basic block. Okay, we will not look across basic blocks. We will study one interesting example of this, and then we will study another example where things may work better if we actually look across basic blocks. If we look at the whole control flow graph, let's say, of a function, and then try to perform scheduling. One may say that, okay, fine, I can even expand the scope further and I can look across functions and try to optimize my schedule even more, which will be beyond the discussion today. Okay. Alright, so let us say I have a program where I have already performed register allocation, I have already performed instruction selection. So I already have assembly code generated along with the registers. So let's say the code looks something like this. I have a load instruction, and let's assume that if I have an instruction like this, opcode destination source. Okay, so you move things from source to destination like this in our assembly over here, let's assume. So if I have an instruction like this, how to read this? It says add 0, this thing is an offset, add 0 to the content of the register R1, you would get some address, load the value from that address into register R2. Okay, so can you give me an example of a register which is usually used to add offsets to? Stack pointer, right? So you can assume R1 is acting like the stack pointer. If you are with x86, you have this %ESP register as we had seen in an example earlier. So let's assume R1 is like the stack pointer. You add offsets to the stack pointer to get access to multiple variables in my stack frame and read from the memory location which is supposed to contain the value of that variable, whether it's on stack or it may be an object, so it may be on the heap and so on, right? Let's say I have more instructions here. Store into the memory location that you obtain by adding 4 to the content of register R1 the value of the register R2. And let's say I have more instructions like this. They have been generated from some high level code which I have already performed code generation for. Okay, so then there I have an add. Let's say add syntax is like this: R3 R3 R4 means add the contents of R4 into R3 and store the result into R3. Then I have 3 more instructions: add R3 R3 R2, then store the result of adding store the result in R3 into the memory location that you obtain by adding 12 to the content of register R1, and finally let's say store into the address obtained by adding 0 to the content of register R7 the value of R7 itself. Okay, it's like star A equal to star A, the last instruction like we had seen earlier. So let's say this is a sequence of instructions produced by my code generator, and now I can schedule these instructions. I can try to schedule these instructions better. Let's also now consider some interesting features about our hardware. Let us say on my hardware I take one cycle. If I execute an add instruction, an arithmetic instruction in cycle I, then I can schedule the next instruction in cycle I plus 1. So add does not cause a lag of more than one cycle, let us say. Whereas let's say I am loading something from memory, it may take more time, whether the operand is in cache or whether it's in a register, whether it's in the memory and so on. So let's assume for simplicity that if I load something from the memory, it takes 2 cycles for me in order to find the result in the loaded register. So if I have an instruction load R2 comma 0 of R1, it means the result of performing the load, first I have to compute what is 0 plus R1. I'll get some address, then I'll find whether that address is in the stack or the heap, if it's there in my cache, whether I have a miss or a hit. Let's just assume for simplicity all of this requires 2 cycles to get the result from there into the register R2. So if somebody like the next instruction, what does the next instruction do? Which register's value does it depend on? R2 here. It requires the value of R2 to be stored into over here. When will it get the value of R2? Let's assume after 2 cycles. Okay, so let's create edges here. We'll draw dependence edges here labeled with the amount of delay needed for executing the next instruction. Let me repeat, we'll draw edges here between, let's assume these instructions are different nodes of a graph. I have 7 nodes in this graph, and an edge in this graph represents a dependence, and the label on the edge tells the amount of number of cycles I need to wait before scheduling the next instruction. Okay, so after a load, what we said is we have to wait. Let's take a different color maybe. Let's say I have to wait for 2 cycles because the result of this load is required by the next instruction. So before I can schedule this one, I need 2 cycles, let's say. Okay, is there any other instruction that needs the result produced by this load instruction? Let me give some numbers here so that it's easier for you. Let's say this is I1, this is I2, this is I3, this is I4, I5, I6 and I7. So we had a data dependence from I1 to I2, and since I1 is a load instruction, it's of 2 cycles. Is there another data dependence from I1 to some other instruction? I5, right? So I5 requires the result of R2. Let me write it more clear. So this is R2. It requires the result R2 which is produced by I1. No other instruction produces I1. So in the program order, since it's in a basic block, the previous def of that value R2 is coming from I1. So I can draw an edge from I1 to I5 as well with what label? 2. All right. And then similarly, do we have any dependence from I3 to somewhere? I3 has the next load instruction. Yeah, I3 to I4. I4 requires R3. So I3 to I4, I should insert a delay of 2 cycles. Does I5 also require the same R3? No, right? Which R3 is loaded, which R3 is used by I5? Where does this R3 come from? Does it come from this load? No, it comes from this previous guy. And for add instructions, we need to insert a delay of 1 cycle. Let's say load requires more time. So let's create a data dependence here, but let's put the label 1 over here. Can you help me add more data dependencies if they exist? I5 to I6, because I5 produces result in R3 which is needed by I6. So there is a 1 cycle delay here. Anything else? I6 to I7, why? There is no, at least there is no dependence or direct dependence there as I mentioned till now, right? But let us assume that since both are store operations, right? Store will require the same part of memory to be accessed in order to, so it would require access to the bus which writes to the memory, for example. So let us say, irrespective of what we are storing to, each store has a, if I have another store after it, I can only schedule it after 1 cycle. So if I start scheduling I6 here, I have to wait for 1 cycle before scheduling I7, because it involves the same circuitry, for example. So this is again, this is just our model here. Now, are there any such more assumptions that we need to, any such more dependencies that we need to create here? I3 to I5, no. So again, this R3 is obtained from I4, not from I3, right? So there is no direct data dependence here, but there could be, in the, I would claim that there could be indirect data dependencies here. So my claim is I need to add more edges to this graph. Why do you, can you guess why? You remember pointer analysis from yesterday? Yeah, so if I refer to A dot F at some place and I refer to B dot F at some place, can I guarantee that they are different objects, they are the fields of different objects? No. Correct, unless we know that A and B cannot point to the same object. If A and B may point to the same object, then A dot F and B dot F does not mean that they are different references. A dot F may be the same as B dot F, and if A and B are pointing to the same object based on our yesterday's discussion, right? So what it means is, here it is possible that adding 0 to R1 gives me the same thing as adding 4 to R1. Or rather, it's possible that adding 12 to R1 gives me the same thing as adding nothing to, as adding 8 to R1, for example, creating some dependence over here and so on. Because I do not know what are the values of R1 and R7 here, which means adding 4 to R1 may give the same address as adding 8 to R7, unless I know that their locations are already more than 4 bits apart, for example, 4 bytes apart, for example. Right? So there may be more dependencies here which are indirect dependencies like pointer dependencies from yesterday's class, and hence we need to take account of them as well. So let's look at one, and then you would be able to help me out with more. If I am loading the value of a memory location that I obtained by adding 0 to R1, content of R1 in I1, it's possible that I am also writing to the same memory location in I7 by adding 0 to R7. Because I don't know the value of R1 and R7, and hence since they would again require access to the same memory, let us say there is a delay of 1 bit. Before I could put a store onto the same address, if I am loading from the same address, let us say our hardware requires us to wait for 1 cycle. So I would create a dependence between I1 and I7 with the label 1 over here. Are all of you with me? Are there more such edges that we would have to add? What about, let me give you a hint, what about things starting from I2? In I2 I am storing to some content, some address that I obtained by adding 4 to R1. 4 plus R1 might be same as 0 plus R7 again. So we had said you cannot perform a store to the same memory location. You cannot perform a store until you have finished the previous one. At least you have spent 1 cycle after the previous one. So there is a dependence like this as well here, let's say. Do I need to create an edge from this store to this store? No. Why? 4 plus R1 is always going to be different from 12 plus R1. It's the same R1 as you said. So 4 plus R1 will be different from 12 plus R1. But 4 plus R7 might be same as 12 plus R1, for example.
R3 and 4 plus R1 might be same.
That does not matter, right? R3 will give me some value. I'm just copying that value. I'm not performing a memory read over here. It's already there in a register, right? The memory access is being performed over here. 12 plus R1 will give me some address and I want to store into that address in the memory, right? Are there any more edges that we should add like this? Can 8 plus R1 be same as 0 plus R7? Yes, we don't know. So we should add an edge from I3 to I7 as well. Oh, I erased it. We should add an edge from I3 to I7 as well, again with the label 1. Are there any such dependencies that still exist? I2 to I3, I2 to I3. No, 4 plus R1 is guaranteed to be different from 8 plus R1. Right? They are not going to be the same memory location and hence I need not worry about them. So let's say we have covered all the dependencies here. Some have, how many of them have a label 2? 3 of them, I1 to I2, I1 to I5 and I3 to I4 have label 2, and then there are a few more edges. So all these are data dependencies over here. We have no control dependence here. Can a control dependence exist within a basic block? No. Why? Correct. So it's a single entry, single exit thing. If there is a control dependence, I'll split and create a new basic block. Right? I cannot have a control dependence within a basic block. The only thing that I can have here is a data dependence. So such a graph is called a data dependence graph. Okay. Each instruction is a node of that graph and an edge between two nodes in this graph indicates a data dependence, and we also have a label saying how long should you wait before scheduling the destination of that edge after scheduling the source of that edge. Are all of you with me? Okay, so now let's say the compiler has this information available. Now what can a compiler do? How can you, so let's look at it intuitively. If you go to the Dragon book, you would see an algorithm, proper defined, well defined half page algorithm for what we will do right now, but let's do it intuitively first. I have this sequence of instructions along with the dependencies in the form of a data dependence graph. Now what should I do to schedule? What do I want to achieve by creating a schedule of these instructions? I need not necessarily execute all these instructions in order, in the same order. I am allowed to execute them in a way that I may finish in fewer cycles. Can you suggest how should I prioritize instructions by looking at this data dependence graph? Sure, those that are independent can be scheduled in any order, so that gives me some flexibility.
And also such that they don't interfere with these cycles, the stalls.
Right, of course, we need to make sure that we are not scheduling an instruction before some instruction which it depends on. Anything more? Yes?
Schedule that instructions first that on which most of the other instructions depend.
Very good. So we can also give more priority to those instructions for which many others are waiting. right? So here let's try to create such prioritized schedules. Okay, this is called this basic block scheduling is called prioritized basic block scheduling. So let's create some priority orders here. Let's look at the graph and let's try to find out what should we prioritize first, of course while respecting all other constraints and data dependencies. So if I start from I1, if I start, let's say, executing from I1, what can I execute after I1? I can execute I2 after I1, right? So let's say I execute I2 after I1, and after I2, well, there is no dependence over here, so this part is almost independent. After executing I2, I can execute I7. So if I have a path in this program that goes from I1 to I2 to I7, can you tell me the length of this path in terms of the delays that are required? So 2 plus 1, 3, and let's assume 1 cycle would be needed for the last instruction to get executed. So total, let's say this path takes 4 cycles. If I execute this path is independent of the other instructions. I can execute I7 after I2 directly, I don't need to wait for anything else, and this path would take 4 cycles. Now let's look at some other paths like this. What if I start from I3, because I3 doesn't have any predecessors in terms of dependencies, right? It can also be a first instruction to start with instead of I1. So if I instead decided to start with I3, and let's say I keep following this I3, I4, because there is a dependence, then I5, then I6, then I7. So if my schedule is I3, I4, I5, I6, I7, see, why am I putting them like this? I cannot execute I7 before I5. Because of these data dependence edges, this path needs to be executed in order. What would be the number of cycles needed to execute this path of instructions now? 2 plus 3, 5, and 1 for the last one. So 6 cycles, let's say. Are there any more interesting paths? Oh, from I1 I went directly to I2. Instead of that, maybe I could have followed some other paths from I1. Let me follow I1, I5. Yes, there is an edge here which is also with a high label, so somebody has to wait longer for it. So let's say I choose I1, I5, I6, I7. So I'm just listing down all the paths from the root nodes of this graph. There are 2 root nodes here, as you can see, and I'm trying to list paths from those root nodes. How much would I incur now? 2 plus 3 plus 4 plus 1, 5, right? So 5 cycles. Now, like this, you can list more paths. Let's say we generate these paths on demand. We start from some root and we keep generating some such paths. Let's say again we have a greedy algorithm. We don't generate all the paths. Enumerating all paths may be exponential in terms of the number of nodes and edges I have in the program, in the data dependence graph. So let's say I don't generate all of them. I start generating some of them starting from the root nodes until the end node, let's say. And now I see that, oh, this path looks interesting, isn't it? This is the longest path. Maybe I should start executing from this path. Won't that make sense? So let us say we generate some paths and we take the path that has the highest cost, or we can say which is the most critical path here. The most critical path seems to be I3 to I7, since it's the longest in terms of the number of cycles required to execute all instructions in this path. So maybe I should start by giving priority to instructions in this path. Okay, let's do that. So that's the heuristic, let's say, that we pick over here, and let's start scheduling instructions now. So let's say I have options in each cycle to pick an instruction to schedule, right? In the first cycle, let's say I decide to schedule the first instruction in my critical path, which is I3. I3 is load R3, 8 of R1. So let's say, as the compiler, I decide to schedule this instruction, load R3, 8 of R1, the address obtained by adding 8 to the content of R1. This is scheduled in cycle number 1, let's say. Now again I have to make a decision, what to execute, what to schedule. See, already the compiler has reordered things because there is no dependence between I3 and I1, I2. Hence, I don't need to wait for executing I1, I2 before starting to execute I3, and I decided to execute I3 based on priority over here. Now, should I pick I4 or should I pick I1 now? So I have two options here. Either I pick I1 at this point, I4 at this point of time, or I go to another path and pick I1. Why? Why do I have these two options? What's the length of the path remaining from I4 to I7? 4. Here there was a delay of 2, right? I3 to I4. I have already scheduled this. So from this I have the length of the remaining path in this path is 4, and I have another path whose length is 4. So I have two options now again with the same cost. So if in my priority order there are two paths or subpaths in this case that have the same cost, which one should I start now? One which covers, well, maybe that's not ideal, because more number of roads doesn't matter until you finish executing. If a certain path has 5 load instructions, let's say, I may want to give more priority to that over another path that has 10 instructions but all are adds because they require 1 cycle, for example. So the length is more. Yeah, why so? Yeah, so let's look at, I think your reason makes sense, and another way to look at it would be, oh, somebody will have after I1, even if I pick I1, the next instruction in that path will have to wait for 2 cycles before getting scheduled, right? Whereas in this I3, I4 path, if I schedule I4, the next one will have to wait only for 1 more cycle. So maybe I should prioritize the load over here because somebody has to wait for 2 cycles. So even though both paths have, so when both paths have the same length, how do I decide my priority? I may, let's say, put a heuristic here which says, oh fine, I should not just worry about the next cycle, I should also see a bit ahead and find out, okay, if I execute one of them later, somebody will have to wait 2 more cycles for it and I would cause delays later on. So let me prioritize those instructions which have more delays for the next instruction. In this case, it's just load, but different instructions may have different costs associated with them when we work with a larger set of ISA, larger ISA over here. So in this case, in our example, it looks like since both have the same cost, taking I1 may be better over here. So let's schedule I1. Are all of you fine with my reasoning here? Right. So let's say I schedule I2, I1, which was this. Yes. No, so we have already scheduled I3 from here, right? Does I4 cause a delay of 2 cycles? No. After I4, no, if it uses the result of, okay. Oh, I did not mention, so is it? Oh yeah, there is another reason here. Yes, as Jayashree points out here, I4 cannot be scheduled at this point, in fact, because as the edge denotes here, after I have scheduled I3, I need to wait for 2 cycles before the result is available for I4. Yeah, that's another good point here. So was that the point you made? Yeah. So I4 needs to wait for 2 cycles, so I can't actually schedule I4 over here. But let us assume this was schedulable, and if both the paths have the same length, you may still want to prioritize those paths for which you may incur more delays in future, which is again I1 over here, right? Starting from I1. So of course, yeah, you cannot execute, that's a good observation. I cannot schedule I4 anyway, so I'll go with the other path and schedule I1. This is a simpler example then, but I have already given you insights on a more complicated example, let's say. So because of which at cycle 2 I cannot schedule I4, so I went to the other path which also had length 4 and picked I1, okay, and I have scheduled I1 over here at cycle number 2. Now number 3, what should I do? Let me come back to my original path, let us say, okay, because that was the one I had given more priority to, and in the other path anyway, after I1 it's I2. Can I schedule I2 immediately? No, again there is a delay of 2 cycles over there. So let me continue with my original path here. After I3, I can schedule I4 now because 2 cycles are over after executing I3. So let's put in cycle number 3, let's put I4, which was add R3, R3, R4, then in cycle number 4, I can either put I5, can I? Yeah, I can either execute I5 or I can execute, where did we go? I1, I2, I7, or I can execute I7. Which one would you like to prioritize here? So what's the length left? After I4, I still have I5, I6, whereas after I2, I just have I7. So the length of the critical path is more in the second case again. If you add it up, it's 2 plus 1 plus 1. So let me schedule add R3, R3, R2. Now in cycle number 5, which instructions are left? I have finished, let's keep ticking here. I have executed I3 and have I executed I2? No, I executed I4 and I have executed I5. Right? Now either I could execute I6 or I could execute I2. Both are store instructions. Right? After I6 I have to wait and then I have to execute I7. There is no real, is there any dependence here? Yeah, is there any dependence here? The instructions left to be executed are I2, I6 and I7. Is there a dependence among them? Yes, I7 should be executed after I6 and I7 should also be executed after I2. So I2 seems to be, again, I mean, you can decide. Here there is no real reason for you to not schedule I6 before I7. I7 depends on both I6 and I2. So I have to execute one of them. The dependence is still of one cycle each. So I could just pick any of them. Let me just stick to my critical path. My critical path was I1, I2, I3, I4, I5, I6, I7. So let me pick the next instruction in this sequence, which is I6. What was I6? I6 was store 12 R1 R3, so I could decide to schedule it here, store 12 R1 R3, and then I may decide to schedule I2 because I7 depends on I2 as well, so I may say store 4 R1 R2, and finally I can schedule store 0 R7 R7 and so on. So I obtained a schedule over here, and how many cycles will it take to execute? 7 cycles, right? If I instead had scheduled the instructions in the same order, I would require more cycles than 7. As you can see here, there is a delay of 2. If I just executed them in this order, I would have to wait for 2 cycles at 2 places. I would have to stall my pipeline basically because of these constraints, and I would have required 9 cycles, let's say, instead of 7 cycles. So I saved time by generating a better schedule. And what was our algorithm here? We created a list of priorities for all the paths starting from root nodes of my data dependence graph. First I made the data dependence graph, then I created priorities based on the delays imposed by my hardware, and then I started giving priority to my most critical path. If I cannot schedule the next instruction in my most critical path, I went to the second path. When there is a tie, I chose something by looking one step ahead and see who will wait more because of this instruction, and based on that I resolved ties over here. Is this an algorithm you think we can implement in a reasonable compiler? Right? So it's instead, if you decided to explore all the paths, enumerate all the possibilities, all the orders, and then decide the best order, maybe it will allow you to work out in 6 cycles instead of 7. But maybe it won't be worth the effort. So people usually find that a priority based scheduling like this, which does not try to find the best order but just tries to clear ties away by giving immediate priorities, by looking ahead locally instead of looking ahead globally and trying to find which one would give you the best outcome, works fine. So most compilers work with this kind of algorithm instead of doing something which is more complex, which requires a lot of computation before deciding the best schedule. Okay, any questions? This is like a greedy algorithm, right? Because at each step we are looking at the local minima, right? What minimizes, in fact it's greedy from 2 places. If you see your book's algorithm, it doesn't even enumerate all the paths here. Let's say it enumerates one path and the second path. it starts working based on these two paths. If it feels that, oh, both paths are stuck, it will generate one more path. So it even generates these paths greedily in some sense. So it's greedy from two perspectives, from choosing what to do next as well as for generating paths themselves. Okay, it's like on demand, just to make it faster. Any more questions? Mm-hmm.
So basically, we are only looking at the next instructions, like how much time we are requiring. This is our way to make it faster. But there can be other lots of ways in which we can do it.
Correct. So enumerating all of them would require you to work with an exponential problem space, which will make it NP complete.
So every time we add a new instruction to the new schedule that we're making, we have to also check if all the dependencies are met.
Correct. You cannot schedule an instruction if it has to wait for some other result. Right? If you schedule it anyway, the result will not be available. So there is no point scheduling it if it cannot be scheduled at this point. Give the slot to some other instruction that can be scheduled at that point. Yes.
So, like here we have pre-ordered it.
Mm-hmm.
When the processors are out of order,
Yes.
again it will jump on its own.
That's a bit different. So here the compiler has already taken care of the out of order execution possible in the processor. If you think about it, we didn't enforce too many constraints here. We didn't talk about write buffers and operand forwards over here, but a typical compiler would take care of those aspects of the hardware as well before deciding a schedule.
Possible schedule will be the possible out of order execution.
Yes, yes. Right? Even though it's possible that the hardware, irrespective of what the compiler told it to do, it has some new features that it doesn't take care of, and then the hardware decides to do something more fancy at the lower end. Right?
It could negate the effects of whatever was.
Yes, that's what we were discussing in the beginning, right? It's both of them need to work in synergy many times, because if you propose an algorithm that's already making things worse for the particular hardware, the hardware doesn't see. The most interesting thing is the hardware doesn't have the whole program available. It doesn't have the budget, it doesn't have the memory to look at the whole program or a large portion of the program. It makes decisions based on very small scope. Right? Whereas a compiler has access to the whole program, it can look behind, it can look forward, it can find out what functions may be executed in future, what might have been executed before. So it is expected that a compiler would produce a better schedule than the hardware which does not have information about the whole program. Does that make sense? But if the compiler knows what all a hardware can do and then takes care of that while generating a given schedule, it's able to utilize the features provided by the hardware better, because the hardware will not be able to look at the whole program. We'll look at more examples. Okay. Any questions? All right. So now let's move to one more tiny example here, with which we will cover global scheduling. Global scheduling just means across basic blocks. Okay. Many compiler passes use the word global to mean that they are not just looking inside a basic block, but they are looking across basic blocks. So see, within a basic block, we were able to reorder instructions. We changed the order of instructions from I1, I2, I3, I4, I5, I6, I7 to I3, I4, I3, I2, I4, I5, I1, I6, I7, something like that. So we changed the order from the given program order. But now, what if basic blocks are usually small, right? Few instructions, then there is a branch, you go somewhere else. So what if after I finish scheduling inside a basic block, I still find that there are hardware resources available which are lying free? But whenever you have a jump from one basic block to another, observe that you need to wait for some branches outcome. Right? There you split because you have to wait for some branches outcome before going to the next basic block. So can we still do something better here? Can we reorder things across branches? That's the point here, to utilize the hardware better. So let's look at an example where the answer is yes. Okay. So let's say I have a basic block with the following high level instruction, then we'll perform register allocation. Let's say at the high level it's like this: if A equals 0, then go to L. This, let's say, is my basic block B1. Okay. After this I have the false branch, if it is not equal to 0, then I execute an instruction C is equal to B. Let's say this is the basic block B2, and then I have a basic block B3 as well, where I have an instruction E equals D plus D, and let's say this is executed irrespective of whether this is true. My code is something like this, let's say. Alright, so it's just an if branch. Let's say if A is not equal to 0, do this, and irrespective of whether it is 0 or not, after executing that branch, execute E equals D plus D. Let's say this is my code here. And now what do we do first? We'll do register allocation. We'll do instruction selection in some order, sometimes before, sometimes after. Actually, I did not ask you an interesting question. You have studied SSA form, right? Okay, so then I'll ask you a question later on. So let's say this is my basic block, and after doing instruction selection plus register allocation, let's say I obtain the following code. Let me write it in the next page. I have done instruction selection and register allocation here, and let's say I obtain the following code for each basic block. Within B1, I had, okay, let me write some outputs here. After doing register allocation, let's say A is decided to be kept in register R1, B in R2. How many variables do I have in this code? 5, right? So let's say each of them has been given a different register. If each of them is given a different register, are there any data dependencies in this code? No. A, B, C, D, E all are independent. There is no indirect access over here. So let's assume that all of them are independent of each other data wise, but they are dependent based on the control here. There is a control dependence from B1 to B2. Okay. So let's say after performing register allocation and performing instruction selection, I get the following code. For if A equals 0, go to L. Let's say I do the following. I load what's there, where is A assigned, which register is A assigned to? R1. So let's say my code generator does something like this. Get the content of R1 and store it into register R6. Why R6? Because until R5 I have already used up registers. So let me use R6 for the result of loading the value of A. Now I want to check whether it is 0. If it is 0, I need to move it, I need to jump to some branch, some go to. I mean, I need to jump to the label L, let us say. So let's say I have an instruction here, branch if equal to 0, R6, if it is equal to 0, then branch to L, or not to 0, whatever. So if it is 0, if A equals 0, go to L. Let's say this was L. Okay, true. Okay, so now there is one thing interesting here. Let us say we have also performed basic block scheduling already. These are the only two instructions in the first basic block, right? Load A, check whether it is 0. If yes, then branch to some other block. Now, if these are the only two instructions here, based on our basic block scheduling example from the previous slide, if I execute this instruction at cycle 1, in what cycle can I execute this instruction? 2 or 3? It's a load to R6, and this instruction requires R6. So how many cycles delay needs to be there here in between? 2 cycles. So which means if the first one was scheduled at 1, the next one is scheduled at 3. And there is no other instruction inside this gap, right? There is no other instruction in this basic block, which means what happens at cycle number 2? What do I schedule at cycle number 2? Nothing. I can't do anything. So that cycle is a no-op. And this is my, wait, I'll just use the same color here. Okay, this is my basic block 1 after performing instruction selection, register allocation and instruction scheduling. This is my basic block 1, B1. All of you with me? Now let's look at basic block 2. I have C equals B over there. So how do I translate C equals B? C has register R3, B has register R2, and I do some instruction selection based on my ISA. And let's say I also perform instruction scheduling within that basic block, based on basic block scheduling as we have seen before, which looks something like this. At cycle number 1, I load the content of R2 into some register R7. Let's say I have enough registers for now. R7, R8, R9, R10, all are free, let's say. And since it's a load, finally what do I want to do? I want to store the result back into C. So I need to generate a store instruction, and that store instruction reads the value of R7, and where does it store it? To C. C is assigned register R3. So let's say this is written like this. Some conventions will, some architectures will require you to specify an offset here. So what offset can you write? If writing some offset is compulsory before these accesses, then you can, before these accesses, you can just write 0 over here, 0 R1, 0 R6, depends on the structure of my assembly. Okay, if it requires some offset, you can just write 0 in this case. Now again, can I schedule this store at cycle number 2 within basic block 2? No, it requires the result R7, which is produced in 2 cycles by the previous load instruction. So again, this is at cycle 3. What happens in cycle 2? Again, no op, let's say. So whenever I can't schedule anything, let's say I insert a no op instruction just to indicate that don't do anything in that cycle, you're lying idle. And this is my basic block 2, B2. Let me not draw it exactly at this place, but let's move it a bit below to show the order hierarchically. And this is B1, this is B2. What about B3? In B3 I do E equals D plus D. So I have to first load D into the register R4 where I had assigned, which I had assigned for it. No, I have to read D from the address in R4 into some register before I could perform addition. So let's say in cycle number 1 here I do load and I put into R8 the content of register R4 where D is there. After doing this, I need to add, right? I have to add D into itself and put the result in an E. So I should insert an add instruction. In which cycle can I put that add instruction in? 3 again, because the result is in R8. So let's say I have a no op again at 2. At 3 I have add R8 comma R8, and let's say the result is also stored in R8 itself because D is assigned the same register. We have seen if you do D plus D and the result is in D, you can do the same thing because of it. And then and then finally I need to do E equals the result. So you can just do here, can I schedule that store operation into E at cycle 4? Yes, because add has just a delay of 1 cycle, so I can do store into the address stored in R5, which is the register assigned to E. In that address I want to store the content of R8, and this is my basic block 3 after performing basic block instruction scheduling, instruction selection and register allocation within the basic block. Now note that we had a false here, a true here, and an edge like this over here as well, right? What does it mean? If I execute, now I have to schedule these basic blocks in some order. If I just execute these basic blocks one after another, if the false branch is taken, what would be the order in which I execute these blocks? B1, B2, B3. How many cycles would I need now? 3 plus 3, 6 plus 4, 10. If I instead schedule, if let's say the condition is true, because I don't know what would the condition be. If the condition is true, I would execute B1, B3. How many cycles would I need then? 7, right? 3 plus 4, 7. So I would need a minimum of 7 cycles and a maximum of 10 cycles to execute this program if I just do basic block scheduling. But we see that there is scope to improve here. Oh, there are these no ops, 2 cycles lying idle. Can I reorder instructions across basic blocks and do something better? So in order to do that, let's make some observations here. First, we observed that there is no data dependence among B1, B2, B3, right? Second, can B2 be executed? Can any instruction, or rather in general, can B2 be executed before B1? No, because it's control dependent on B1. Can B3 be executed before B2? Yes, it's not dependent on B2. Can B3 be executed even before B1? Tell me, is there any data dependence between B3 and B1? Is there, if there is no data dependence and whether the branch is true or false, I need to execute B3 anyway, right? Which means B3 can be executed in parallel with B1. There is no data dependence. I can choose any instruction from anywhere and schedule it, isn't it? If B1 and B3 are not dependent on each other, which one should I prioritize first? That's a trick question. If B1 and B3 are really independent of each other, which one should I prioritize? I am looking at the instructions. The compiler can look at instructions across multiple basic blocks, across the whole, across even functions and so on. So if these are if these are not data dependent, these are not even control dependent, anyway both of them have to be executed irrespective of the path we take. Which one should I prioritize? Which one should I try to start with? Well, there is no control dependence between B1 and B3. That's okay. We are not doing any branching here. Okay, fine. Okay, your point is, so but then that's for the true branch, right? Think also about what if the false branch is taken. Would you be start any execution in B2 unless you know the outcome of this in general, right? So there is another block whose execution will remain pending if I have not figured out this branch, isn't it? Right? So there is another block here which will remain pending here. So maybe I should prioritize B1 first between B1 and B3, just because executing some instructions of B1 will allow me to decide whether B2 needs to be scheduled or not. Yes. 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 So let's decide that. Let us say I execute all 4 here, then I execute all 3 here, 7, and now I decide that the control flow, that the branch is false. I would execute those 3. I'll get 10 again. I was getting 10 in the worst case. I would still get 10. Yeah, I'm not able to hide the latency much, right? So if there is, so let's say this is again a heuristic decision, right? But intuition wise, I would argue that if some block waits on you, you should execute that block. You should execute that block first. Yeah, most likely it's just like 7 to 10 instructions. They'll be in the same cache block. Yes, sure. Your reasoning is right. So Jayashree says, would anyone like to argue and say, tell Jayashree that no, we should not schedule B3 first? Jayashree's point is, she wants to come up with a heuristic that says, if something has to be executed before, I should finish its execution beforehand. If something definitely needs to be executed, she wants to prioritize later instructions first, which will definitely be executed. But what about the first instructions, Jayashree? The idea is these are all independent. These also have to be executed. These also have to be executed. Nobody else depends on their execution. Somebody depends on their execution. Yes. Yes. Exactly. We will do that in fact. So let me just bring in one more observation that will probably help Jayashree also visualize why do we want to prioritize B1 here. There is a no-op sitting there where I can start somebody's execution. Can it be only B3 or can I execute something from B2 also before? Does the whole of B2 depend on B1 really? If I have a free cycle which is there here and which is there here as well, if I have a free cycle, can I not speculatively execute this instruction? Since it's just a read from the memory, it's just a read, I am not writing to the memory. I'm not making any changes. What would happen in the worst case if I preempt this, if I prefetch, or not prefetch, if I pre-schedule this instruction in some sense? In the worst case, we would have wasted a no-op cycle. No-op cycle was anyway getting wasted. But what would be good if I have finished the execution of this instruction? Exactly. If the condition is false, I can directly execute this instruction 3, which is also a memory operation, because I would have already finished the execution of this load in those 2 cycles. Yes. We are not losing anything. If we don't take, we are not losing anything because it was anyway no-op cycle. Same thing, if you decided to start with B3, you could have fit that load instruction in this no-op cycle as well, because there is no data dependence. But now you won't know whether you can execute 3 or not immediately, right? If you instead went with B1 and finished this execution in this no-op, immediately at the next instruction you know whether you should go and execute this third instruction or not, and now you have more options. You can decide to schedule either this or this based on what circuitry is available. Make sense? So let's try that. We have these observations. What are the observations? No data dependence among any basic blocks. B2 is control dependent on B1. B3 can be scheduled in parallel with B1. No control dependence, no data dependence. B1 can be prioritized, should probably be prioritized before B3 because B2 depends on B1. And load in B2 can be moved to B1, but store cannot be moved, right? Load can be moved to B1 itself because there is a no-op cycle over there. So let's consider these observations now, and let's add one more thing over here just for making it more representative. Let's say my hardware can execute 2 mem operations in parallel. Let's say the circuitry has been made more elaborate so that I can schedule 2 memory operations in parallel. I can perform 2 loads in parallel, let's say. Yes?
I have a question. The store that's happening at the end, like the fourth statement of B3,
Yeah.
would that in any way cause any what do you call dependency or some overwriting for? I'm asking similarly with what Jayashree was saying, trying to schedule B3 before B1. Does that store operation may overwrite the load that may happen in the first statement?
No, not really, right? There is no data dependence is what we concluded in the beginning. A, B, C, D are independent. None of them are pointer variables. All of them are independent.
Sir, rather than we putting B2 blocks load into B1,
Mm-hmm.
can't we put B3 blocks statement 1 into no-op in B1?
We could. So again, we have the question: should we try all the possibilities and then just come up with the best possible answer, like the previous case? Exactly, right? It's perfectly possible that when we develop an algorithm, a greedy algorithm here with a local optimization, it's possible that if I would have enumerated all possibilities, I might have gotten a better schedule.
Because in the worst case, we can waste a no-op in no-op, but if we load B3, if we load instruction of B3 there,
Mhm.
so that
What would I have achieved?
that worst case would have been eliminated.
Why so?
Because
So okay, let's try it out.
even the no-op won't be wasted.
Let's try it out. I put this instruction over here. I cannot execute anything from here yet, right? In the next one, what would you like to schedule? So we have already consumed 2 cycles and done with both the loads, let's say. So let's keep counting. Maybe it gives a better answer. So let's schedule both of them. Then let's say we check the branch because somebody is depending on it. Cycle 3. Then what do you want to do next? Third of B3, let's say, cycle 4. Then so cycle 4. Then first of B2, cycle 5.
Then in no-op we get last of B3.
Yeah, so last of you have to wait for this load to happen here, so you can't schedule this one. So in this no-op, last of B4. So how many? 6, and then this one 7, right? So you might be if we counted rightly, I think you might be able to come up with 7 or 8 still.
Anyways, we can't do instruction first load from B2 into the norm of B1 because, like, speculatively, when we execute the first load, what are the register that the address we're picking up? Is it is a sensitive information that should be picked only when the control flow reaches there?
That's supposed to be a guarantee given by the hardware. That, oh, if you load something speculatively, nobody else should be able to read it. If the hardware does not guarantee it, the hardware is not secure. From the compiler's perspective, that's supposed to be a guarantee given by the hardware, that if I am executing something speculatively, nobody should be able to read it. And a secure hardware will guarantee it. I mean, Spectre attacks, and so I'm sure I know where you are coming from. So some hardware do not give that guarantee. They allow some attacker to read some speculatively loaded content and then infer malicious information and so on, right? So that's insecure hardware. From a compiler's perspective, that's okay, isn't it?
This is the only information the compiler has, right? But the
Yes.
compiler will not know the exact path that is going to be taken.
Correct.
So it's just heuristics at the end of the day.
I don't know, why do you say it?
Because, like, it's like
What path will not be known by the compiler?
like we are trying to just come up with an approximation, but we
Yes.
don't know all exact paths taken.
Which paths?
Speculatively, what path will be executed at the end of the day.
Compiler is telling what path to execute speculatively by performing instruction scheduling.
Yeah, I think my understanding is completely.
Okay, we'll talk about it more. Any other questions? Yeah, 1 and 2.
Even after merging B1 and B3, we'll have to keep the branch as the last instruction, right? In the merge block.
Well, let's see how do we merge. But yes, you can't. Well, not really. You can't. You don't need to keep it as the last instruction.
So it's a basic block.
Forget about basic block now. Who cares? A compiler constructed basic blocks out of the programs, and its job is to reorder things and finally give you a linear schedule. Let us say, right? We are anyway doing this at the end. We studied all optimizations yesterday. Now we can get rid of basic blocks. We are just reaching execution now, isn't it? But your question is good. If you performed scheduling before, so that's where my question comes from. A question that I promised to ask. There is an interesting dependency between register allocation and instruction scheduling. Over here, we have performed register allocation and then we are performing instruction scheduling, right? What if you did the other way? Can you think of a case where performing instruction scheduling before register allocation would be better, and vice versa? In that case, you need to keep those basic blocks alive for register allocation to happen later. That's one requirement, but there is a different trade-off. Think about it until I take another question.
Do we need to consider topological ordering?
If there is a control dependence, yes. Right? If there is no dependence, then we don't care about the order of basic blocks as per the topology of the control flow graph. Make sense? Okay. Think about my previous question, but now let's try to finish this example and go for our tea break. So let us say we also have one more carrot given by the hardware here, which is that hardware can execute two memory operations in parallel. Okay. Now let's take advantage of that fact as well and try to produce a schedule in as few cycles as possible. So let us say I have at cycle 1 the possibility of scheduling two instructions now, and one of them, since B1 and B3 can be executed in parallel, let us take what all of you said. If the hardware can actually say that, if the hardware allows me to execute two instructions in parallel, let me not prioritize any of them. Let me schedule them together. Let me take one load from B1, load R6 and what was it, R1, and let me also schedule another load here from B3, because there is no real order required to be maintained between B1 and B3. So let's say this is my first cycle of the newly constructed basic block B1. Okay, I have pulled one instruction from B3 into B1 already and put it into the first cycle. What can I do in the second cycle now? There is one more load here. Loads are the most expensive ones here, right? If you make critical paths across loads, multiple people will wait on loads for 2 cycles. So in the second cycle, is this load independent of the other 2 loads? Yes. So let me speculatively schedule. This was our no-op cycle. Let me speculatively schedule the second load here, which was load R7, comma 0, no, let's just say R2. Is there any other execution that I can execute in parallel now? Is there any other execute instruction across those basic blocks that I can schedule right now? No, right? The store depends on the load as well as its control dependent on the branch. The branch is dependent on the load's result. Load requires 2 cycles. Similarly here, the add is dependent on the load's result and load requires 2 cycles. So we can't really do anything. This part is a no-op, blank, let's say. In cycle 3, what can I do now? I can execute this add, I can execute this branch. Can I execute this store? Not yet, because it's control dependent. So I can actually utilize this cycle for both the slots, and I can decide to schedule branch R6 comma L, and the second instruction could be add R8 comma R8 comma R8. Am I still in the same basic block? Can I continue in the same basic block, or now do I need to create a new one? No, any 2 operations including memory operations can be executed in parallel, let's say. Yeah, okay, that was the statement I wanted to make. So let's say all of this is my basic block 1. Why should I split the basic block now? There is a branch, right? So now what is left? Let's say in the false branch, if the condition is false, what do I need to execute next? Store from the basic block 2. We'll do one more magic over here. In cycle 4 here, we'll just finish in 5 minutes and go for the tea. Store, let's say R3, R7, and I have one more slot. Can I schedule something else here? Well, there is nothing to be scheduled in B2 over here. We'll do some magic soon though. If this is true, what can be executed next? Yeah, so this is B3 and this is B2. The last statement of B3, which is store. This is cycle 5, store, no, cycle 4 itself, right? Yeah, this is cycle 4 because this is in another branch. And now can somebody improve this even more? See what would happen right now, I would incur this. And because of that, this will not be 5, in fact, this total will be 5 if the false branch is taken, right? If the true branch is taken, the total will be 4 cycles, but if the false branch is taken, the total will become 5 cycles. Can I not do some magic here and finish off in 4 cycles? Yeah, can I copy that statement into the empty slot of B2? Because anyway that has to be executed. So let me remove this edge then. And now, as you said, we are playing with the basic blocks now. We have reorganized the basic blocks. Let me remove the edge between B2 and B3 and just add a copy of this instruction over there. And what would that allow me to achieve? It will allow me to finish execution of the whole program in 4 cycles, irrespective of whether the condition is true or false. Right? Of course, if the hardware did not allow you to execute 2 instructions, I think you would incur a cost of 6 here, 6 or 7. I think 6. You would be able to schedule that load here. So one more cycle will be gone for it and one more here. Yeah, so 6 or 7, one of them. If you schedule it after that, then it will still be 7. But the answer that you were trying to get by scheduling all of B3 before B1, if it also gives you 7, then maybe they just both give the same answer. It's also possible that by exploring all the paths you may get 6, or in this case 3, I don't know. But if you don't want to execute, rather enumerate all the paths, you will come up with a heuristic based greedy algorithm, let us say. And what was the algorithm here? Can somebody help me point out? Like in the basic block version we had an algorithm. Here I didn't tell you the algorithm. What algorithm did we use inherently till now? The most expensive. What do you mean by expensive here? Correct. So if somebody, if some, again we took the same, we used the same idea, right? If there were, hi Arun, if there are two, your next instructor is already here. So if somebody is waiting for someone for a longer time, we tried to prioritize those instructions, in this case the load over here. But we were still making local decisions in some sense. We did not enumerate all the paths and then made the decision like we did for basic block scheduling, right? And of course, different hardware may have different, real world hardware may have more complex assumptions to make here, more complex constraints here, and then based on them your compiler can generate even better schedules and so on. Any more questions before we break? All right, so this finishes the part that you need to go into session 3 today. But in session 2, after the break, we would talk about JIT compilers a bit, and which will be a bit of digression from this, but you would, I'm sure you would continue with instruction scheduling in the afternoon perhaps, right? That's the plan, right? Yeah, so this is some topic we will revisit in the winter school furthermore, and I can make my life easier by saying direct more questions on scheduling to Professor Dr. Arun here, and leave me with it. We'll go to JIT compilers in the next session. Okay, see you.